Hello, everybody. Welcome to the second part of Lesson 7. In this section, we're going to be discussing inferential statistics, statistics used to predict outcomes. And so there are many different types of inferential statistics we could talk about. It could go on for a much longer time, but beyond the scope of this course. So we're going to focus on the big ones, the main ones that you might come across in reading the research literature that you might find helpful in your careers as you go along reading research articles. So just a review. Descriptive statistics are used to describe data collected in a research study. We talked about this in the last lesson. Frequencies, percentages, means, standard deviations. But inferential statistics are used to make inferences or predictions from the sample to the population the sample was taken from. Now, with this inferential statistics, they're used in research design. For example, let's say a researcher wants to examine if variables are correlated with each other. So you do a correlation or an association between physical activity and obesity to find out if there's any type of association. Researchers want to compare groups to examine any differences that may exist. For example, differences in a physical activity participation between males and females. Do females do more physical activity versus males, or vice versa? Or researchers may want to examine the effectiveness of a treatment on an outcome of interest. For example, the effects of a particular novel exercise program on visceral fat. But the underlining aspect of inferential statistics is to infer or to predict if there's any cause-effect relationship between an independent variable and a dependent variable. Now that's very difficult to do in maybe a smaller study, the cause and effect, but at least would give you some idea of a relationship or a prediction of one and the other. So that's what we're going to be talking about. Now, the first statistic we'll be talking about is Pearson correlation coefficient. And you use a correlation to determine an association between two quantitative sets of intervals or ratio data. Researchers compute this correlation coefficient. Now, there are several different types of correlation coefficients you could use, but the more common one you'll come across is the Pearson product moment correlation coefficient. And it's symbolized by an italicized lowercase r in reports. Now, there's a negative correlation and a positive correlation. A negative correlation can range from -1 to -0.01. And this indicates that if the value of one variable is high, then the value of another variable is low. So, for example, you might take someone who has a high amount of physical activity each week, and it might be correlated to a negative LDL, or lower LDL cholesterol level. So as physical activity increases, a person's LDL levels will decrease. Well, that'd be a negative correlation. Now, the positive correlation can range from 0.01 to 1.0. And this indicates that if the value of one variable is high, then the value of another variable is also high. So, for example, someone who does a high amount of physical activity, they may have a high rating of self-esteem, for example. So as physical activity is high, so is self-esteem is high. That would be a positive correlation because both variables are high. Now, here's an example of a Pearson correlation coefficient output from SPSS. And again, you can use the data that's on Blackboard, the fake data that is on Blackboard, along with accessing SPSS through the ITS. Again, there's a tutorial on the Blackboard about how to access SPSS through the SIUB ITS. But let's talk about how, and you can do this analysis with me, and we'll show a video in just a moment of how to do all this. But here is an output of correlations. You have a Pearson correlation, minutes, weeks of physical activity versus self-reported global self-esteem. And what this 0.67, here is the output, or here is the correlation that was outputted. And you can see that it has the asterisk, and that indicates that this correlation is significant at the 0.01 level. And again, you can see here's the significance level as well. So what this means is that with a significant level of 0.01, that this correlation we can be pretty confident that it is true. There is some type of correlation. Now, one thing you can do is you can take the correlation and you can square that. It's called R squared. And R squared is a statistical measure that represents the proportion of the variance for a dependent variable that is explained by an independent variable or variables in a regression model. So what that means in this particular case, that we take 0.67 and we square it, and it means that 44% of the variance seen in self-esteem can be attributed to moderate vigorous physical activity. And it also means that 56% of the variance in self-esteem is due to other factors besides moderate to vigorous physical activity. So to put some context to the correlation, we have this continuum here, and here is for correlation. If you remember, it goes from 0 to 1 or 0 to -1, and it outlines what a weak, moderate, or strong correlation would be. Now, you're not going to really, normally we wouldn't get a perfect correlation, but generally speaking, the higher the number up to 1, the stronger the correlation. Again, it can be positive or negative in terms of the correlation. So again, in our example, we have 0.67. That would fall within the realm of about moderate to strong correlation between the two. Now, there might be situations you can have a significant correlation, but it might be a very weak correlation, say maybe 0.2. Although it's significant, it would really be, there might be most likely other factors besides the factors you measured that could be explaining the association between or having an effect on something. So just keep that in mind, that again, the negative correlation all the way up to -1 and positive correlation up to a +1. So here's a video of how you would go about doing a correlation, Pearson moment correlation in SPSS.
Simple. So we would have our data set open here, and the correlation that I looked for here was between our variable MVPA, which is in minutes per week, and self-esteem. And just a refresher, MVPA is something that could have an absolute 0. Somebody could do absolutely no moderate to vigorous physical activity simply by laying on a bed for their entire life. And this would be an example then of ratio data, whereas this would be interval data. We don't expect that there would be an absolute 0 for self-esteem. Somebody you would hope would have some sense of self-worth at some level in their personal self-concept. So to analyze this, I hit analyze. I'm just going to go down here to where it says correlate. That's my option. And I want to do a bivariate correlation. I'm looking at 2 variables. And now I'm just going to choose the variables that I want. And we already know that I'm looking at minutes per week of moderate to vigorous physical activity. So I'm going to move that over. And I'm also going to look at self-reported global self-esteem and move that over. I don't need to do anything with option style bootstrapping or anything. I do want to make sure that I'm doing the Pearson correlation. If you're interested in, well, when would be a special case that I would use one of these others, like a Spearman row you might use with when you've got ordinal data that you've ranked or something, but for this purpose, we're just going to stick with the basic Pearson correlation coefficient. We're going to leave it as a 2-tailed test, so that way it could pick up whether it's positive or negative. And we're going to flag significant correlations here. Hit OK, and minutes per week of moderate to vigorous physical activity is, like you saw on the PowerPoint slide, positively correlated with global self-esteem, and that is a significant correlation at the 0.01 level here. Okay, so let's...
So that was a video that discussed the Pearson correlation coefficient using SPSS. A little bit more information about this coefficient, some considerations. As we mentioned, a perfect correlation of -1 or a +1 between variables are not probable in a sample or population of people. And the reason for this is, let's say you took a scale measuring the effect of physical activity on self-esteem in an entire population. It would only take one individual to rate them a 9 out of 10 versus 10 out of 10 for that correlation to fall out of the 1 1.0 or a negative 1.0. So it's a highly unlikely you'll ever get a perfect correlation, especially when working with human participants. Now, another consideration is that Pearson correlations are not suitable for nominal and ordinal data. However, dichotomous variables that have two different branches, such as gender, are often analyzed using Pearson correlation as long as the other variable is interval or ratio. And the reason for that is that in gender, you can indicate a 0 or a 1 for male and female, and then you can be able to do a Pearson correlation. And again, you might see this in your literature review, so it's just something to keep in mind as we go along. And lastly, it's important to understand that correlation coefficients are not suitable for assessing the effectiveness of interventions or to predict changes in a variable based on changes in another variable. Again, you're just looking at an association. The strength of that association is what you'll be looking at. So keep that in mind as you're reading some of the literature for your project. Now, the t-test, it's the most commonly used to test the null hypothesis that two values, means, are not significantly different. And this is common in research in exercise physiology or the health sciences when you might be determining maybe the relationship or the significance of a established instrument versus a new instrument, and comparing the two means, the values between the established instrument values versus maybe a new instrument that's being tested. So trying to compare those two means. Now, the ability of the t-test to capture significant differences is affected by three things. The first is that larger sample sizes can lower the risk of differences being due to a sampling error. So again, as we talked about, the greater the sample size, the greater the chance that it reduces that variability and it reduces any sampling error that might have occurred. But again, you have to take into consideration the cost and time to work with that size population. Now, the second is that the larger the differences between the means of the two variables, the lower the risk of differences being due to a sampling error. So in other words, by simple observation, if you have two means that seem they're really far apart, you can infer that there's a greater chance that those differences are not due to sampling error. Now, the last is that the greater the variation in the population, the higher the risk of differences being due to a sampling error. So the more heterogeneous that they are, the greater the chance that they're going to have a greater variability in the sample. So if you have a more homogeneous sample size or sample to draw from, you can be assured that the differences being due or may not be, or reduce the differences due to sampling error. So, again, what your population that you're going to get to draw from is going to be important in terms of reducing the sample error. So here is a t-test output from SPSS, and this is an example where we wanted to test if there was a significant difference in moderate vigorous physical activity between males and females. And what we determined was that there was, because of the fact that it was the significant two-tailed or the t-test indicated that the significance was at 0.066, so it was above or greater than 0.05, it indicates that we can fail to reject the null hypothesis that there is no significant difference between the males and the females. So in other words, in this particular case, that once you fail to reject the null hypothesis that there is no significant difference, it would indicate that there potentially could be some differences between males and females. So let's look at another video of how this was calculated using SPSS.
I'm just going to go to Analyze, and I want to compare means. In this case, I'm going to use an independent samples t-test because I'm comparing by gender. Now, if I wanted to compare basically the means on two things between one sample, so I'm going to compare mean anxiety scores on one measure and mean anxiety scores on another measure within the same sample, I could use a one sample t-test to see if those means significantly differ from one another. But in this case, I'm going to be comparing genders, so I'd use the independent samples t-test. And this is going to give me a grouping variable, and my grouping variable, is gender. And I'm going to define those groups based on what I have made them. I dummy coded them as 0 and 1 in my data set. So I'm going to put that, and you can see that here. Gender 1 was male, 0s are females. So that's my grouping variable. And then for my test variables, again, I'm looking at whether the time spent in moderate to vigorous physical activity differed significantly, so we move that over. I don't need to do anything with my options or bootstrapping. I'm just going to click OK. And so here we see our means for the groups, so we can look and see, well, yeah, the mean is different here. But we also have a pretty large standard deviation for both of them, which violates that assumption, at least, that we don't have, our sample doesn't seem to be very homogeneous in that regard. And then our minutes per week of moderate to vigorous physical activity, our t-statistic is here, and this is our significance level for a two-tailed test at 0.066, meaning that we failed to reject the null hypothesis. Okay, so back to...
Now, another statistics is the one-way ANOVA. And a one-way ANOVA is like the t-test that we just talked about, but in that it tests the null hypothesis that means are not significantly different. But where it differs is that it is able to test the difference between more than two means. So instead of like the t-test, you just had group A, group B. But in ANOVA, you can test more than two means. Now, ANOVA is very common in health science research, so it's important to be aware of this. Now, ANOVA will tell researchers if there are significant differences in the means overall, but it does not tell us which means are significantly different from one another. For example, we don't know if group A, group B, or group C is greater than or less than one another. And the way to test this is you have to do a follow-up comparison, a multiple comparison test. It's also called a post hoc analysis. So to think about it this way, ANOVA tells you that if you have three groups, that somewhere along the way, that somewhere there's a significant difference between at least two of the means. But it doesn't tell you what two means. You'd have to do a follow-up post hoc analysis. Just keep in mind when a researcher has only two means to compare at a single time point, they can use a t-test or an ANOVA, as both will produce the same p-value. So just keep that in mind. But again, it's important to be aware of an ANOVA. It's very common in health science research. Now here is a output, SPSS output of a t-test versus a one-way ANOVA. For two means. And what we have is, you notice that with a t-test, you have the significance is 0.066, and here is the t-value. Using the ANOVA, we have, again, 0.066, but this just reports a f value. Now, something to keep in mind that the more t-tests that you do increase the chance of a type 1 error. If you remember back, a type 1 error is failing to reject a true null hypothesis. So typically, to avoid this, ANOVA is really good if you're trying to compare two different means over and over and over again. It tends to help reduce that the chance of a type 1 error. So let's take a look at using a one-way ANOVA for three or more means. In this case, we're looking at some data using minutes of physical activity, but amongst different income levels, low, middle, and high. And what we see here is using the ANOVA table, the printout, it shows that there is a significance between physical activity and income value. But what it doesn't show you is, it doesn't tell you where, in terms of which income values differ from each other. So in order to determine where the comparisons might lie, we do a follow-up post hoc analysis. And what that means is that now it's going to be comparing each income level with the other two income levels. And so you have low versus middle. And what this shows is this is the difference between the low income versus the middle income. And then here's the significance level at 0.033, so it's less than 0.05. So that would be significant. Here's an example where they're doing a comparison between low and high, and the difference now is a negative 115 between the two. So again, that significance was less than 0.01. So you can do all the comparisons between the other two, and to get the results. This just happens to be that all of them are different, but there might be situations where, let's say, low and middle might be different, but let's say middle to high may not be a significant difference, and this would tease that out using that post hoc analysis. So let's look at a video of how to calculate this using SPSS.
So first I'm going to go back to my data set. Again, let me show you here. I have income dichotomized as 3 different levels. So there's 0, and I'm sure there's 0, 1, and 2. And I'll just go ahead and show you what the variable view of that looks like too. So I have my variable name here. I have that there's no decimals with this. I label it as income level, and in values, I assign the values here. 0, low, 1 for middle, 2 equals high. Now, how do I go about that? Typically, I would actually have the individual's income to then reclassify them or categorize them according to their income. So I might actually have another column over here that says actual income, and they might put in there 25,000 or 30,000 per year or whatever it may be, and then I would classify them based on their reported income as low, middle, or high. And so I have my income variable here, and I have my physical activity variable, and I'm going to go to Analyze, General Linear Model, and I'm going to do a univariate analysis. And now again, my fixed factor in this case was income level, so I want to put that in here. And income level has three different levels for it. And then I was comparing minutes per week of moderate to vigorous physical activity, so that goes in as my dependent variable. I'm going to leave model and contrast alone. If I wanted to, I could plot this out as well, so I might want to plot income out on the horizontal axis. And then I go down. I don't want to do any post hoc analysis. I only have one group, but I will come down here to options, and I'm going to display means for income, compare main effects, and then because I have multiple comparisons here, I'm going to go ahead. I'm comparing 3 different groups. I'm going to use a Bonferroni for this. I'm going to go ahead and get my descriptive stats. Estimates of effect size, I'm going to put that in, but that's something that we'll go over in the next presentation. And let's hit continue, okay, and just go through our output real quick that you saw. So I get my means and standard deviation. Well, this tells me what my between subject factors are. Income level, 0, 1, and 2. 0 stands for low, 1 for middle, 2 for high, and gives me the breakdown of how many people in my sample fall into each group. And then here's my means for income and the standard deviation for that variable. So this is their mean time, minutes per week spent in moderate to vigorous physical activity. So even visually, we can see that the high income group, it looks like it's significantly larger. It also has a big standard deviation though, but we look at that and go, holy cow, they're a lot more active, but we don't know from this if they're significantly more active. We need to do the statistical analyses. So this is the, we're going to go on down to the pairwise comparisons because that gives us better information to make up our mind about this. So this is the comparison that I showed you, low compared to middle and then compared to high. Here's the mean differences and whether they're significant or not. Oh, it does look like I probably used a different post hoc analysis or pairwise comparisons analysis Bonferroni on this. I think maybe in the initial one I ran, I maybe used the least squares difference or whatever, but that's irrelevant at this time. The significance would still be there, but it's just a little bit different value here, and the mean differences stayed the same. So this is how that looks graphed out, and if that's one way, if we wanted to visually represent these differences to see, you know, that it looks like the minutes per week spent in moderate to vigorous physical activity certainly does differ by income level, with high-income individuals appearing to be very much more active. But again, it's these significance tests up here that give us that important information in determining whether or not this difference is actually significant.
So let's move on to a two-way ANOVA. Now, a two-way ANOVA is used to test for significant differences in means when the participants have been classified in two ways. For example, physical activity status and gender. So in this case, you'd want to find out, is there a difference between genders and the amount of physical activity they may be doing. So a two-way ANOVA will answer two questions for researchers. One, is there a main effect? Is there a significant difference or effect overall? Is there somewhere happening? In this case, is there something happening between physical activity and males and females? That's the first thing that a two-way ANOVA would tell you. The second is there an interaction? Does the difference depend on another variable? So in this case, does the physical activity status differ between males and females? And that will tell us that. So the main effect is there a difference between just gender and physical activity status? And the interaction will tell us which gender, if there is a difference between physical activity status and the gender. So do males differ in physical activity status, or do females? So that's what this two-way ANOVA will tell us. So please keep in mind that like a t-test and a one-way ANOVA, the basic two-way ANOVA is not used to assess the effectiveness of an intervention where there may be two or more groups and the data were collected at more than one time point. Let's go on and talk a little bit more about this two-way ANOVA. So here's a two-way ANOVA using some of the fake data that's on a Blackboard. And here, what we're trying to test with this is the effect of meeting or not meeting physical activity guidelines by gender. So determining, does it matter if you're a female or male in meeting or not meeting the physical activity guidelines? So here is, again, the means and standard deviations of those not meeting versus meeting. You can see in terms of the self-reported global self-esteem. So what it's saying here is the main effect is looking at physical activity guidelines overall. Is there some type of difference of meeting the physical activity guidelines? The second is there a main effect of gender? Is it differ by the gender? Does it happen? So we're looking at physical activity guidelines and if there might be a difference by gender. And finally, this is the interaction, determining the physical activity guidelines by gender. Does it matter the gender you're in terms of meeting the physical activity guidelines? So the first thing we look at is the main effect. Is the physical activity guidelines, is there a difference in terms of meeting or not meeting the physical activity guidelines overall? And you can see there is a significant difference. So there seems to be some way of indicating that there is some differences in terms of meeting or not meeting the physical activity guidelines. So again, this would indicate that there is a main effect of physical activity guidelines on our self-reported self-esteem. Okay, so it's saying that physical activity guidelines, in terms of meeting or not meeting them, does have an effect on self-esteem. Now, looking at the effect of gender, it would indicate that it does not appear that gender, male or females, has any effect on self-reported global self-esteem because it's greater than 0.05. Now, looking at the interaction effect of physical activity guidelines and gender, it appears that there tends not to be any difference or interaction, that it doesn't seem to be a matter if you're a male or female in terms of meeting the guidelines and the effect it might have on self-esteem, because again, this is greater than 0.05. So the take home here is it appears that the effects of physical activity on self-esteem is independent of gender. It doesn't matter if you're male or female, the effect on self-esteem is the same. Now, the repeated measures ANOVA is another type of statistic, and it's used when a researcher wants to compare means obtained from one or more groups at multiple time points. Let's say baseline, middle, and end of a particular time. So it might be baseline, 4 weeks, and then at 8 weeks. in order to test the null hypothesis that the means obtained at the different time points are not significantly different. So you're trying to find out, essentially, let's say a group might be on diet and over 8 weeks, and do they change over that 8 weeks? And so you would be using a repeated measure ANOVA to determine if there's any difference between baseline and middle, and then middle to end, or between baseline and the end. And that would be a repeated measures ANOVA, one-way ANOVA. So keep in mind, as with a regular ANOVA, the repeated measures ANOVA will tell researchers if there are significant differences in the means overall, but it does not tell you which means are significantly different from one another. For example, we wouldn't know, let's say there's a significant repeated measures ANOVA, less than 0.05, but it won't tell you where it's occurring. You don't know if it's time 1 between time 2, or is it time 1 and time 3, or time 2 versus time 3. You would have to do a follow-up post hoc analysis in order to determine or tease out exactly which time points differ. So here's an example of looking repeated measures ANOVA using one group over time. So here would be the BMI at baseline, middle, and end, for example, of a study. And here are the mean scores that they obtained. Now you wouldn't be able to determine if there's any significant differences between them. So that's where you would come with a ANOVA. And the first part is just the repeated measures ANOVA would tell you that looking at BMI, you would look at the fact over here that it's less than 0.05, which would indicate that there is some significant difference happening during this baseline, middle, and end. But what it doesn't tell you is where is it happening. Is there a difference between baseline and middle, or is it between baseline and end? So that's where you would need to do a follow-up pairwise comparison. In this case, we normally would do a Bone-Ferroni post hoc analysis that you can get through SPSS. And it's simply what this is just telling you is, again, this would be comparing the baseline to middle, and then looking at, that's the actual differences. So basically taking 35.52 subtracted from 35.07, and that would be the value that you get. Well, this is a significance level, and you can see it's less than 0.05, so that would indicate that there is a significant difference between baseline and the middle of this study. And then you would do another comparison looking at baseline versus the end, and there's the difference between them, and there's a significance. It would be a significant difference. And you can continue to do that with all the other comparisons. So let's look at a video of how this can be calculated using SPSS. Now the volume might be a little tough to hear, so make sure you turn it up if you're having difficulty.
So again, in my data set, I have BMI 1, 2, and 3. I'm going to go to Analyze, General Linear Model, Repeated Measures. Let me reset this so you can see what I did. Now, one thing that actually I should have done different, and I'm going to do it now in the example, and it's not going to mess you up, I hope, is instead of calling my within subject factor name BMI, which is basically my dependent variable, I'm going to put time, because I know I'm comparing BMI at 3 different times, and I have 3 different levels, so 3 different times that I'm comparing BMI. So time is a little bit easier to interpret sometimes, I guess. So we'll add that. My variable name does not contain an illegal character, unless I put a space on accident. Try it again. Okay, define, and I go in here and I'm going to pick BMI, and I'm going to highlight all 3 of these, being they are in order. Because they're in order, I can do that. If they weren't in order, I'd have to do them one at a time. And I'm just going to click this arrow here, and it's going to automatically put them in as my time 1, 2, and 3 dependent variables. I don't have a between subjects factor. I can skip model and contrast. If I wanted to plot this, I could say, let's look at BMI over time on the x-axis. Continue there. And then we won't do any post hoc analysis, being I have one group. And then options, we go here. I want to look at display means for time, compare main effects. We'll choose a standard adjustment there for the Bone-Ferroni. Just descriptive statistics. We can get we'll save estimates of effect size for the next time around. And I'm going to go ahead and hit continue. My model is ready to go, so I hit OK. And as you see, I've got my within subjects factors defined here. So at time 1, 2, and 3, it's BMI 1, 2, and 3. BMI is shown here, my descriptive statistics. So BMI at pre-test, post-test, and at 12 months, my standard deviation, and so forth. Now, one of the things I can look at again is my tests of within subjects effects. I can look down here. It's the same thing as what's up here, basically, in terms of significance. The Wilks lambda tells me that, that's a standard one to go to. The effective time on BMI, Wilks lambda shows us there is a significant effect here. Same thing down here. Effective time is significant, and pretty much everywhere I look, I'm seeing that there is a significant effective time, but that doesn't tell me where, at what point does BMI significantly differ. So let's go down. Again, here's my estimates again, this time with standard error instead of deviations. And here's the pairwise comparisons table that you saw on the PowerPoint slide. And again, this most important things I typically would want to look at is what the mean difference was, and was it significant. And here's the profile plot. So visually, I can see that from time 1 to time 2, BMI looks like it decreased drastically, and from time 2 to 3, it is starting to creep back up. And who knows, if we were to collect data again 6 months later, maybe it is all the way back up to where it started, or maybe even higher. And that wouldn't be that uncommon in weight loss studies, so we might expect to see something like this in an actual intervention trial for weight loss, where we would see some people rebounding in terms of their weight. Now
here's a repeated measures ANOVA using two groups, where you have, again, looking at a treatment group and a control group, and looking at pre-test, post-test, and then following up 12 months later. And here's the treatment groups, their averages. You can see they lost weight pre to post, and then they gained a little bit of weight, but they pretty much were able to maintain it, whereas the control group pretty much stayed the same throughout the entire test. Well, now we want to find out, is there any significant difference within a group? In other words, the treatment group, did they actually significantly change? And then is there any significant differences between the treatment and the control group? Well, we first look at time. So this is going to tell us, is there any differences over the time within the group? And so what this is telling us is, did anything change between the treatment group over time? And it just shows, with the significance of less than 0.05, that over time there appears to be a significant difference in the treatment group's weight, or BMI. And this tells you, is there any difference over time between groups? So is there an interaction between the type of group you're in and the BMI loss that you might have? And again, this indicates that yes, the type of group you're in did affect the BMI changes that we're seeing. Well, then you can do a test of between subjects. So here's what we're doing here. We're doing a little bit more of determining the differences between group. Is there a group effect? And then again, this just shows that it did matter, that there is a difference between groups. So in other words, saying that the treatment group differed between the control group throughout the study. So you can conclude that these differences here over time were significantly different between the treatment group and the control group. Or put another way, the treatment had a significant reduction in BMI in the treatment group, but there was no changes in the control group. So let's show a little. This next video is going to describe how these tables were generated using SPSS.
For repeated measures ANOVA with two groups. So I go back to Analyze, General Linear Model, Repeated Measures. And let me reset this. Actually, let me show you real quick too. Here's where my group variable is. And I just grouped them as 0, 1. So you can see group assignment. The values I assigned to them is 0 equals treatment, 1 equals control. Okay. And so go to Analyze, General Linear Model, Repeated Measures. My factor again, I'm going to put as time, and I'm going to say we have 3 levels because I have BMI at 3 different times. Add that. I'm going to define my model now, and again I'm going to put BMI in for my within subjects variables. Now I'm going to use group assignment as my between subjects factors. So this is how I'm going to compare between subjects, is by group assignment. Now, quick note on what is these covariates. I could turn this into a repeated measures and COVA if I felt that gender significantly, because gender maybe was significantly associated with physical activity or BMI, BMI at baseline, then I could include that as a covariate. And really what I would be doing is controlling for the effects of gender on BMI when I'm doing this between groups analysis, this between subjects analysis. So that would turn this into an analysis of covariance model, but I'm not going to worry about doing that now. I'll skip model and contrast. If I want, I can plot this. I can put group on the horizontal axis, time on separate lines, add that interaction there, so the group times time interaction, and I'll show you what that looks like after I run the analysis. Post hoc analysis here, again, I only have 2 groups, so I have 2 levels of the independent variable, and I don't need to worry about that. Now, if I had a 3rd level, maybe a different group who did some other type of intervention, then I would worry about doing a post hoc. For options, I want to get my display the means for time, compare main effects, and again, Bonferroni, descriptive statistics, estimates of effect size. I'm going to come back to that. I'm going to show you it in the next presentation. So my model is pretty much ready to run. So I'm going to run this, and you'll see it defines my factors here, or my dependent variables here at the different times, as well as my between subjects factors, group assignment. 0 is treatment, 1 is control. And then here's my descriptive statistics for BMI at pretest for treatment and control. And you can do some visual comparisons. And then you move down and say, oh, yeah, it looks like that went down by 3 points or just over 3 points. So maybe something's going on. Maybe our treatment was working. And that difference is still here 12 months later. So it wasn't an immediate rebound, but it is maybe starting to trend in that direction. I can look here again at Wilks Lambda, just the effect of time in general, and we see that there was a significant effect. There's also a significant time times group interaction. And some of this other stuff, if this was a stats class, I wouldn't be more worried about telling you what tests of sphericity mean, but we're just going to stick to the stuff that you need to be concerned when you're interpreting research. And so let's go on to our pairwise comparisons. Excuse me, this is not pairwise, our test of between subjects effects. And so this is the output that's of most interest to us, I guess, is that we see that not only was there an effect of time and the time times group interaction and so forth, but that when comparing the 2 groups to each other, there was a significant effect of group assignment on weight loss, p-value less than 0.01. So going back here, it's the same thing that I reported on here, is that.
All right, so that was a video that discussed how to calculate repeated measures of ANOVA using SPSS. Now let's go to the final aspect of this. It has to do with the practical significance of the study results. So this relates to making decisions on the applicability of the results of the study based on 5 criteria. So in other words, you get your results, and how do you use this results to make decisions, essentially? So the first is a cost-benefit analysis, and the researcher would need to determine the potential benefits of applying the results of the study, and should they warrant the potential cost. So for example, there might be a difference in a change of exercise on glucose values of, let's say, 2 points, but it might cost a tremendous amount of effort and time to get those 2 points changes in glucose value. So is it really worth the amount of the effort and the cost to get that clinically maybe meaningless changes in glucose values? The second is crucial difference. So that means that the potential costs are worth it if applying the results of the study would lead to a crucial increase or decrease in an important outcome. So let's say, for example, a study has to do with treating breast cancer, and they find that this very expensive protocol does reduce mortality rate. So in this particular case, because even though it might cost a lot, the benefit is that it reduces mortality rate. So this might be where people would get behind this and feel that the potential costs are worth it. The other is that client acceptability. Now, this means that whomever the study results would be applied to should find them acceptable to avoid a negative reaction. So you would have to weigh the results and determine if will clients actually go with this. And it could be they might not feel comfortable because it might go against social norms or particular belief. So the researcher would have to determine if the benefit is there. Another is public acceptability. It is best if the application of the study results would not lead to a major opposition from segments of the population. For example, in stem cell research, this has been a hot topic in the United States of whether or not stem cells should be used in certain areas of research. So that would be something where you'd have to weigh public acceptability of the results. And finally, ethical implications. No matter the statistical significance and affordability of applying the study results, it should not violate any ethical standards or laws governing treatments of whom the results would be applied to. So that would be something that the researcher would need to consider when applying the results. So when making a decision as to the practical significance, you need to take these into consideration. And so be aware of these, and it might be wise in some cases to talk to legal counsel or to talk to other researchers to make the decision. In your particular your program or your report that you'll be doing for this class, you may not need to consider some of these or many of these. However, if you're, something that you would want to try to avoid is any type of ethical implications. But these are the things that you would want to consider when making some practical, significant decisions based on the results of a study. Now, this concludes this part of Lesson 7. Make sure that you have a good understanding. Review the video and the notes before taking the exam or the quiz. Good luck.